Okay, so let's start the class today. Okay, so first we have some announcements. Okay, so we'll have a first exam on May the 7th. Okay, so roughly speaking, we'll cover chapter 1, 2, 3, 5, and 6. And we will reserve another room, should be room 501 for the exam. So please come to the physics building for the midterm exam, and please wear your mask. And before the exam, we will email you about your C assignment. Okay, so because we need to put you in a pattern to maximize the distance between students. Okay, so now we are already grading we are putting the homework score on the LMS system, so you can go to the LMS system to check your homework score. And if you want to request a digital copy that is reviewed by the TA, you can send an email to TA and he will send you back the graded copy of your homework. And my apology for the confusion for the homework 3 and 4. So because I didn't delete some of the information on LMS homework assignment, so that I need automatically send out some announcement. So basically from now on, I will not do any announcement on the LMS. So it just serve as a system that you can turn in your homework. So for any problem about the homework assignment, please just go to the new website and see the homework and click it to each homework. It should contain all the necessary information for the homework. And if you still have a problem or confusion, please just email me. Okay. Okay, so today we will start by going through some of the problems in homework 1 and homework 2. Okay, so in homework 2, well, 1, there's a problem about Maxwell relations. Okay, so basically this is from the partial derivatives. Okay, so it's simple. So we assume that all our thermodynamic functions are very nice functions. So you can do all kind of partial derivatives, and if you have more than 1 degree of freedom, the older you take the partial derivative, doesn't matter. So basically they commute. So in mathematics, we know that if there's a function f, it's a function of x and y. Okay, so then basically, if this is a very nice function, then for the second order derivative, I can partial derivative to x first, then partial derivative to y. Okay, so if this is a nice function, then it should equal to if I do partial derivative to partial derivative y first and do the x. Okay, so because they are the same, so sometimes we just write this as a partial square partial x partial y equal partial f partial y partial x, and we just become slightly lazy that we didn't pay much attention to the order in this partial derivative. Okay, so Maxwell relation is basically you start from certain thermodynamic potential. Okay, so if you start from energy, first of all, you think about energy as a function of entropy and volume and the particle number. Okay, and then from this you can take a different derivatives. Okay, so now if I take a derivative with respect to entropy and volume, I can have two different orders. Okay, and then remember, since we also have an n particle number as an independent variable, then we should in principle put the subscript n's to remind ourselves that we keep n fixed during this calculation. Okay, so we assume energy is a nice function, so that means this partial derivative commute. Okay, so this part coming from the calculus. So you have a nice function, then you can do partial derivative and they commute. Okay. Now we need to combine another piece of information. Okay, so we know we can write this in differential form. So that means I have an energy change equal to TdS minus PdV plus mu dN. Okay. So if you are dealing with other thermodynamic potential, then your independent variable can be different. Okay, so that depends on the function you are dealing with. Okay, so from this equation, we know we can derive T and P and mu as the partial derivative of the energy. So that means temperature is partial E partial S minus P is partial E partial V, and chemical potential is partial E partial N. Okay, so now the next thing is we combine those two information, so we see that the partial E partial S on the left would be temperature, and partial E partial V would be minus of the pressure. Okay, so now if we put in this equation, then basically we find that the partial derivative of T with respect to volume at the fixed particle number is the minus of a partial P partial S fixed. Okay, so if you just look at this result, you might look mysterious. You don't know why it is like that. Okay, so basically you just remember that it comes from two facts. One is that this when two partial derivative they commute, so the order doesn't matter. Okay, and another piece of information is that this differential form of this your thermodynamic potential of free energy, you can write as the something plus the d of your independent variable, and from this kind of expression you can easily write down the expression for the conjugate variable. Okay, so here the T and S are conjugate, P and V are conjugate, mu and N are conjugate. So you partial derivative to V, you got something related to the conjugate variable P. Okay, so if you combine those two information, then you get this kind of Maxwell relation. So you can have many different Maxwell relations. So you don't need to remember all of them. Okay, you just need to know that if when you need it, you can derive the Maxwell equation relation in this way. Okay, so now the next problem we are going to briefly talk about is problem 2.1. Okay, so I have a multiple choice problem. Okay, so let's write the Li is your score. Okay, so now if I just do a random guess on this multiple choice question, and then it turned out that you get 70% probability that you get correct. Okay, so now suppose each question has a 10 points. Okay, so what's the average point expectation value of your question I, right? So if you get 70%, that's probability 0.7, you're lucky and you guess the right correct answer, then you get a score 10, right? So that means you have a 30% that probability that you get it wrong. In that case, you get 0 score. So expectation value is 7. Okay, that's pretty simple. Okay, so we know we all also need a square. Okay, so what's the expectation value of the score of your certain question I? Okay, so now again, it's very simple. So if you have a 0.7 probability to get it correct, in this case, what is your score is 10. So what you are going to average is the 10 square of 10, and you have a 0.3 probability that you get 0, and you put the square. So that means your average LI square is 70. Okay. So now we are interested in your total score. So this is very familiar with the your random walk, but that's just in random walk on average on each step. You have half and half probability moving left and moving right. So on average, you are not moving. Okay, here you have a non-zero average. Otherwise, they basically they are similar. Okay, so in the random walk we find that we need to find a correlation between two questions. Okay, so you can ask about what is the joint the expectation value that your question I is correct and your question J is incorrect or correct. Okay, so we see there are 4 possibilities. So both of them are correct. So the probability of a problem I correct is 0.7, and the probability on problem J correct is 0.7, right? So this the joint probability will be 0. Multiplied by 0. Okay. So another possibility is I got the problem I correct, so that I got 0.7 here, but I got a problem J incorrect, so I got 0.3 here. Another is the point I incorrect and problem J correct, or I can both of the problem I didn't do it correctly. Right? Okay, but for the last 3 combination, basically I got score 0. For the first one, then I got the 10 multiplied by 10. Okay, so we find this Li, Lj, the expectation value of Li multiplied by Lj will be 49. Okay, however, we find out this should be I not equal to J, right? Because here in this calculation, basically I assume I and the how you guess on problem I and how you guess on problem J are independent, and the problem is also independent. So basically, so the joint probability is just the multiplication of the 2 probability. Okay, so when I equal to J, so this is nothing but our I squared, which we have calculated here. Okay, so your total score is, if you have n problem, is basically the sum of I from equal to 1 to n Li. Yeah. So we want to have some idea about the variation of the score, so that we standard deviation or variance. Okay? So we know in this case, basically we need to find this standard deviation square would be the expectation value of Sn squared minus the expectation value of Sn and then square. Okay? So now we just need to plug in our formula and try to do the calculation. So again, this whole calculation is basically similar to the random walk calculation. So you just need to copy the calculation and then modify with some detail. Basically, you have a non-zero drift, then you can get to the correct answer. Okay, so since Sn is Okay, so let's let me see. Let's go try to figure out where we stop. Okay, I think we stop around here. Okay, so let's quickly go through. Okay, so basically for each problem you calculate the expectation value. So for each problem the expectation value is 7. Okay, and the Li square expectation value will be 70. Okay, and okay, and the correlation, if I is not equal to j, you can calculate the correlation, and you get this 49. Okay, so this is basically either the expectation value of a single problem or the correlation between two problems. Now we can consider the total score, which is the sum of all problems score. Okay, so what we are interested in is the standard deviation of your total score. Okay, so by definition, it's Sn squared, the average, minus the expectation value of Sn squared. Okay, so now we want to calculate those two terms. We just express them in terms of Li. So Sn is sum of Li. So that means the average is the sum of the average. So that will be 7 multiplied by n, assuming you have n independent n problems. Okay, and Sn squared, you write this is the sum of the product of two sums with a different dumb index. Okay, so now you expand this. So basically, you can decompose it into two types. The first time I equal to I, so you get Li squared, and the second time Lj is not equal to I, so you got the Li Lj. And so here you have n terms. Each term you have an expectation value of 70, or you have n multiplied by n minus 1 terms, and for each correlation you got 49. Okay, so you collect the result, you find the expectation value of S total score squared is 70n minus 49n plus 49n squared. Okay. On the other hand, the Sn is 7n, so its square is 49n. So we see that the n squared term cancel. Okay. So this is again a very typical behavior. Okay, so in this case, we again see that your variance is basically proportional to n. So the standard deviation will be the square root of n. Okay, so now if I have 10 problems, so that means my standard deviation would be something that is 21 multiplied by 10, which is about 1449. Okay, which is about 15. Okay, so that means okay. So now if I have a certain class, I use this example. Okay, so you take the exam and I try to, and after I grade all your exam, I do a statistics. I find the variance is 15 square. Okay, so how do I know if this text is meaningful or not? So we want to. So if it's a random guess, so that generates sort of a certain background noise. Okay, so you want your signature to be larger than your noise. So that means if I can know if you are just do a random guess or you really know the problem and you are doing well. Okay. So if I calculate the variance of the score for this particular class, I find it's 15. So I square it is it's a 15 square, so it's like something like 225. Okay, so here, so now then I can write this. So I can write this is a 20 multiplied by 10 and plus 15. So how do I do this? So this first come from my this sigma of your random guess. Okay, so this is, I can interpret this is the noise, and this is a signal. Okay, so what does that mean? So the random guess is you don't get any signal out of the exam. So nobody's doing not pay any attention or try to prepare for exam. They just all students are just do a random guess. In this case, we expect that the standard deviation, the variance to be 210. Okay, so if variance is larger than that, then I can interpret that is the signal of this exam. Okay, so then we can calculate the signal to noise ratio. And it will be 15 over 210, and this is very small. So that probably means this is not a good exam. Okay, so multiple choice has this kind of problems. Okay, so it's very difficult in general to see if somebody just do a random guess or he's really do the preparation and know how to answer all the problems. Okay. Okay, so now again, let's go back to some random word related problems. So problem 2.14. Okay, so suppose I have a random word that on average I have some drift, so that the average of Li is not 0. Okay. So that means Li average is, let's call L bar, which is not 0. Okay, so if you have just do a totally fair random word, so you have a half change going forward and half change going backward, then you average it. The expectation value for each step should be 0. Now you have some direction that you drift toward that direction, so the expectation value of each step is non-zero. Okay, so then how do I deal with this problem? Then it's very simple. We just subtract the drift. So it's sort of so since this L bar is a constant, then you can think about you put down yourself on a moving frame. Then on this moving frame, the expectation value for each step will be 0. Okay, so you simply shift your variable Li by L bar. Okay, so Li is your original random variable. You shift it by its expectation value L bar. You define LD, Di. Okay, so apparently the expectation value of a Di will be 0. Okay, so by definition, okay, so but what we are interested in is actually the Sn, which is the sum of ILI. Okay. Okay, so I can reverse this. I can write basically Li is Di plus L bar. Okay, so then I have this I basically is the Di plus L bar. Okay, so now if I try to calculate the expectation value for this expression, okay, so now since the L bar is just a constant, so this is equal to n multiplied by L bar, and by definition, the expectation value of a Di is 0, so another thing is 0. Okay, so this is what you accept. if for each step your expectation value is L bar and you have n steps, then you expect that your total distance will be n multiplied by L bar, right? But now what is the sort of the variance? Okay, so what we want to calculate is Sn again minus Sn average square to average. Okay, and this is and we see that this is okay. So now what I want, okay. So how I want to do this is I want to connect this as to something related to Dn. Okay. So what we can do is we can find the variance of a Dn. Okay, so I can think about D. Okay, so D is summation over Di. Right, and this is something like the sum over Li plus L bar. Okay, so basically you have sum over Li bar plus n L bar. Okay, so what do we have? So the first one is nothing but your Sn, right? No, this is a minus. Sorry, so this Di is this is minus. Okay, okay, and this is my Sn. Okay, so then it's very simple. Then basically this is Dn squared is right. So we know this is actually this. If you just expand this, you get Sn squared average minus Sn squared. Okay, so I can calculate, and this is the variance of the original one. Yes, original one, and this is D is the one that you shift you already shift the drift turn. So this for D, for each step of the D, the average is 0. Okay, so that just will be the random what we calculated before. Okay. Okay, so basically, if you have a random walk that with non-zero mean, you just shift it so you have a DI, and then your D mean is 0. Okay, and then which is Li minus L, right? So for this one, we already know how to treat this with this random walk with 0 mean. Okay, so you calculate this, and then you can connect the result for the L and D, and then you can get whatever you want. Okay, so another one is about problem 2.15. Okay, so this is not a very difficult problem. They just try to give you some idea about if the particle is non-conserved. Okay, so for if particle is conserved, then basically we do this gradient expansion, then we get this result. Okay. And if you go back to the derivation, you can see that this term has a prefactor 1. So you can think about this is multiplied by 1. And this 1 can come from that if you normalize your probability, okay, then in general the probability should normalize to 1, right? So if you have a certain distribution of particle and you change that to a and you cannot create or destroy a particle, then particle density integration, you should get the normalization and should be 1. Okay. So however, if you imagine that you can create a particle or you can destroy a particle, okay, so in that case your sort of the probability density will no longer be normalized. So even at the beginning, in the t equal to 0, you normalize everything to be 1. Then because if you destroy the particle, the total population will get less. So your normalization will become smaller than 1. Okay. So now here, if we assume that I can create or destroy a particle at a certain rate, then I can the one of the simplest way to modify the equation is now if instead of normalize this to 1, I can normalize this to 1 plus some rate multiplied by time. Okay, so this will go to 1 to some certain prefactor multiplied by delta t. Okay, so this is sort of account for your particle creation or absorption. Okay, so if you have this, then you can I have this extra term basically. So this 1 was already there if when we assume particle number is constant. Okay, so the only extra term is this. So I can modify my diffusion equation. And it will look something like this. Okay, so originally I'd have this partial rho partial t will equal to a squared divided by 2 delta t partial square rho partial square x squared. Okay, so now I have this extra term, so that means it will have a rho xt. Okay, so this extra term is what we are looking for. Okay. Okay, so now let's go to the more interesting problem 5.4. So it's about the black hole. Okay, so we think about a very simple black hole kind of model. Okay, so we can imagine that we don't need to know all the detail of physics or advanced property of the black hole. So all we need to know is that we can think about this event horizon, and you have a spherical black hole, and the horizon event horizon means that anything that goes in, even the light, if the light falls into this event horizon, then it can never escape. Okay, so I can think about this as a black hole has a certain radius. Okay, so some general relativity told you the simplest solution is that this radius is related to the mass of the black hole. Okay, so we know the black hole appear at the end of the cycle of a certain huge star that you have the mass is so large and it collapses to a so small a volume, so your density is so high, and it collapses into a black hole. Okay, so conceptually you can think about this mass associated with the black hole. Okay? And so for larger mass, your black hole will be, the radius of your black hole will be larger. Okay, so then we want to combine certain information. So first is the temperature of the black hole. So the temperature of black hole I can express in this way. Okay, so if I know the mass, then the temperature is inverse proportional to the mass of the black hole. Okay. Okay, so now we also need another important information, that is energy is mc squared. So we know that in a relativistic kind of scenario, I can the energy is related to the mass. Okay, so for the certain mass, you can generate, since in black hole, you can think about L, the mass is converted into a certain type of energy. So let's write this as capital M. Okay. Okay. So what is the important thing that we want to study? Okay. So specific heat. Okay, so what is not special about black hole? Okay, so the specific heat, we know usually with specific is how your internal energy varies with the temperature. Okay, so for this particular situation, it's easier to calculate the inverse. So I do the inverse of this. So I should expect that if I do partial derivative of temperature with respect to energy, I get 1 over c. Okay. So now I can combine those. So I need to combine the energy, and I need the function of a temperature. I want to write the function of energy. Then I can do this by connecting the energy to the mass. Okay. So I just replace EMC squared, so I can put this. Basically, E is M. You just need to rescale it. Temperature MC squared. Yeah. And energy is nothing but mc squared. Okay, and c is a constant. Okay, so I can think about this as a derivative over m. So this there is something like so they have some prefactor which is positive, and then minus 1 m squared. Right? Okay, so what is the amazing part of this result? My specific key is negative. So negative. Okay. So usually if I put energy into certain substance, I expect the temperature of that substance will increase. Okay. However, if you just throw any information or garbage into the black hole, then basically you get the negative sort of the specific heat, which is quite counterintuitive. Okay. And another important thing is you might already heard about Hawking radiation or Hawking entropy of a black hole. Okay, so how do we understand this from the StatMech we have learned so far? Okay. Okay, so remember that in microcanonical ensemble, I can connect the partial derivative of S entropy with respect to energy as an inverse of temperature. Okay. So if I start from, so the energy is mc squared. Okay, so I can think about everything is a function of m. So suppose I have an entropy, a black hole of mass m. And I assume it start with mass 0 and right, and then also by definition I put the entropy origin there. So S0 is 0. Then I have this formula that change of energy is basically integral over 1 over t of your path. Okay, and remember now energy is mc squared. Okay, so now if you go home and do the calculation, then you'll find the result easily. Okay, so that means I can calculate the black hole entropy. So now I got S. Okay, so now I can write the entropy as a function of m, and you look like that. Okay. So now let's let me see. I want to. Okay. So let's take a 10 minutes break, and let's be back at 2:25. Okay. And I'm sorry about the computer crash in this hour. Okay. See you in 10 minutes. Okay, so let's start. Okay, so now we want to go to another topic. So in this textbook, it's a science homework, and in certain textbook, well, they'll mention this in the main text. Okay, so the problem is about so-called negative temperature. Okay, so this is sort of simple in setup. Okay, so basically you consider a two-level system. Okay, so you can think about you have a spin. So when the spin is up, the system has a certain energy. And when the system is down, spin is down, then you have another energy. Okay, so we can sort of shift our energy level such that the positive energy is epsilon divided by 2, and uh, negative one is negative epsilon divided by 2. One moment, please. Okay. Okay. So now let's first consider microcanonical ensemble. Okay, so in microcanonical ensemble, we want to calculate entropy. Right? So at the fixed energy. Okay. So in this type of calculation, you first want to connect the energy to your energy levels. Okay. So suppose I have n spins. Okay. M is number of cross spin. So the number of cross energy is m. So that I have n minus m. I got the energy minus epsilon divided by 2. So what's your total energy? Your total energy E is epsilon divided by 2 multiplied by m plus minus epsilon divided by 2 multiplied by m minus m. Okay? So it's m multiplied by epsilon minus 2n divided by 2 epsilon. Or Okay, so you can invert this. So what you get is M is energy divided by E plus N divided by 2. Okay, so I can think about this as a number of a state with a process spin. It's a function of E. I can write this. Okay, so you can have a question that if I give you any arbitrary E, then maybe the M you got is not an integer. Okay, so we are going to neglect this small thing. So we can basically, you can think about, you can call the energy you choose has to be satisfy these conditions are such that your number stays integer. Or on the other hand, if you think about, you have the when n go to thermodynamic limit, then your energy become almost continuous. So you don't need to really worry about that. Okay, so then it's actually very simple. So entropy S is nothing but the KB log omega, right? In microcanonical example. So what is omega? Omega is a it's a number of different possible configuration you can have, right? So then this is in this case it's very simple. It's just you have n sign. You have to pick up m sign that you assign a positive energy. Right? Okay, so then this is again n factorial m factorial n minus m factorial. Okay, so then your entropy, you just take this, so it's kb log n factorial n minus m factorial. Now then you can use Stirling formula. Log m minus m plus n log m minus. Okay, and you can see that those constants they got cancelled. Okay, so then you can rearrange it so you can get a certain nice expression for this. Okay, so how do I get the negative temperature? Okay, so in our calculation of ideal gas, we make this connection from our entropy function to the temperature. And our conclusion is that 1 over the temperature should be partial S partial E at the fixed particle number. Okay. So now if you just sort of plug in the formula for the entropy we just got, and what you will find? Okay, so you just do this, and then what you get is KB Okay, so I don't know how to. So for m and n minus m, I first partial derivative to m or n minus n, then partial derivative n to e energy. Right? Okay. So again, if you just collect all the terms, then you can get 1 over temperature will be something that Kb and divided by epsilon and log m minus m divided by m. Okay, so now I can get a temperature then which is proportion to your energy, that is normal and then no. Okay, so now I put this back to okay, good. So this is the result we want. Okay, so how do I make this negative? Okay, so we see that if 2 of n divided by 2 minus epsilon divided by 2. Okay. Okay. So what we need to do is this. Okay, this is simple. So I want I want the log to be negative, right? So that means the ratio is, oh sorry, this is the total energy, not the epsilon, sorry. Yeah, okay, so here this is the epsilon. Here inside I want to connect it to the total energy you have. Okay, so this ratio has to be smaller than 1. So how do I make that happen? It's very simple. So basically I just need to my total energy is positive. Okay, so if my total energy is positive, then this is something smaller than 1 and the log of this is negative, then I get the negative temperature. Okay, so how do I get the total pop? Okay, so I have 2 labels. So this label has energy. Okay, so this is 0. So I have one energy level that is minus E divided by 2. I have another energy level that is plus E divided by 2. Okay, so this is ground state, right, which has lower energy, right? So typically you expect that you put a more and low energy state has more population, right? So if a low energy state has more population, then your total energy should be a negative number because you have a more particle number that has a negative energy, and they are the value is absolute value are the same. Okay, so that means if you have a positive total energy, that means you have a more particle that is in the upper level. Okay, so physically this means some kind of population inversion. Okay, so how do I understand this? Okay, so we see this is basically how the entropy change as you change your energy. Okay, so typically if I'm in a normal system, if I have a higher energy, then I expect that I have more possible combinations, right? Because I have access to more and more high energy state. Okay, so that means your partial S partial E is usually a positive number. Okay, However, in this kind of system, then there's a turning point, right? So imagine the limit that you put everything to be the upper level, then you got the total energy to be m multiplied by epsilon divided by 2. Okay, so once you go to your total energy is positive, and so if you everybody has in the positive, then you have only the omega is 1 because you only have one possibility to fill out all the positive energy site. Okay, so that means when you enter the positive total energy region, when you increase further the energy, the accessible configuration actually decrease until it reached back to 1, right? So your omega function as a function of E, so this is 0. Okay, so when you increase some from the negative to something that to 0, your omega function will increase, so your temperature is positive. That is sort of typically what happened. However, if you go into a population inversion region, then if you increase the energy, actually the configuration number you can access goes down. Okay, so then in this region you have negative temperature. Okay, and then the question is, can you reach this negative temperature region? Yes or no? Okay, and then that depends on your experimental setup. Okay, and now you really need to distinguish if you are working in the microcanonical ensemble or canonical ensemble. Okay, so now if you are working in a microcanonical ensemble, you assume that your total energy is fixed. No, sorry. Okay, so you have to assume that your system is decoupled from the outside, and then somehow you can insert the energy so that you can invert the population. Okay. Okay, so now we can also think about this problem from a canonical ensemble point of view. Okay, so then what is the difference? Okay, so in canonical ensemble point of view, I can think about I have n sides. Okay, so each side I have 2 levels. Okay, so apparently what happened in this side is independent, is decoupled from the what happened over the other side. Okay, so I can think about this as an uncoupled system, right? So I can think about each side as a system. Okay, so that means if I have a partition function for this n side, because this is uncoupled, and this is the one side partition function to the power n. Okay, so what is my one side canonical partition function? I have 2 levels. Then I have to couple to a heat bath. Right, and I assume this heat bath at certain temperature. Okay, at this moment I didn't assume this temperature is positive or negative. I assume it at certain temperature, and I just assume when this heat bath is so huge that when it absorbs energy from your system, the temperature of the bath does not change. But I don't need to say it's a positive temperature or negative temperature. What is my single subpartition function is actually simple. So I have a Boltzmann way. right? Okay, and what is my energy expectation value? Okay, and you can do the calculation. You'll find this is epsilon minus epsilon divided by 2 multiplied by hyperbolic tension of beta epsilon divided by 2. Okay. Okay. So now I'm going to use one particular way which connects to our alternative definition of the entropy. Okay, so in our one of the previous lecture, we mentioned that you can define this non-equilibrium entropy as the trace of your probability distribution log over probability distribution and multiplied by a KB. Okay, because entropy is a positive number, your probability distribution is something smaller than 1, so you get this rho log rho. Basically, you get something that is negative, so you put the extra negative outside, so you get the positive energy entropy. Okay. Okay, so this is in the discrete version. This is nothing but sum over all possible probability pi log pi. Okay, so now I have only two levels, right? So I have a two possibility. Okay, so it's very simple. Okay, so I have a minus kb. My first part is z over beta epsilon, right? And then I log z over exponent beta epsilon plus z minus beta epsilon log. Okay, so I just plug in the probability. So basically, I have this. I have a two probability, and then I can use my Boltzmann way. For example, this one is okay. Okay, so for this expression, it's very simple. I can just calculate, I can expand this. So I have multi terms. So I have a term that is kb divided by partition function. Okay, so if I take the log of this, then I can basically just bring down the beta epsilon or minus beta epsilon. Okay, so if we do the collection, no, what is this KB? Okay, so I bring down this and Yeah, okay, so this is KB. So this is one term. Okay, so if you look at this term and compare to our energy expectation value, and you see that this term goes to E divided by T. Okay, and there's another term which is you have a KB log Z. Okay, so this term is nothing but a partition function divided by partition function, so it's 1. Okay. Okay, so you can combine those results. Basically, you have a one side entropy function would be KB log Z one side partition function plus E divided by T. Okay. So now because you are having an uncoupled system, if you calculate the n side, would be the total entropy will be n minus this, and you can multiply by this formula by n, then you get the n side result. Okay. Okay, so the question is now in this canonical ensemble, can I get this negative temperature region? Okay, so now let's go back to the connection between your total energy and your as a function of your temperature. Okay, from this expression, you can see that I can write, if I start from some small temperature, and I let my temperature go to infinity, so that means my beta go to 0 from plus side. Okay, then if beta go to 0, the hyperbolic tangent 0 is 0, and you have a negative sign here, so that means this also go to 0, but from negative side. Okay, so what this means is you start from something that is normal with a finite positive temperature, and then you keep increase the temperature, then the result you can get is you can only reach the zero energy, total energy state from below, right? So then in this way you can never reach a negative temperature region. So it's sort of like a barrier that before you, that if you do this way, then you cannot reach. Okay, however, there's unless, okay, as I mentioned, when you couple to a canonical heat bath, I didn't assume the temperature of the bath is positive or negative. Now imagine you directly couple your system to a heat bath with negative temperature, and you reach equilibrium. Then in that situation, your system, two-level system, can reach a negative temperature region. Okay, but this is different from that if you have a system that connected to a normal heat bath with a positive temperature, and now you increase your temperature of the heat bath to infinity, then that's it, you get stuck. You can never directly go to a negative zero temperature region. So that is something that I want to mention a little bit, and there are other type of calculation associated with this. Okay. Okay, so before we go back to the quantum mechanics, quantum statistical mechanics, there's one more thing that I want to mention, and it's actually problem 6.6. Okay, so this is not in one of your homework, but that's something that I want to mention. Okay. So it also starts from the entropy definition that entropy okay. So often we heard about we want to maximize the entropy, right? Okay. So basically we want to show that if we write our entropy function as a trace of a p log p, and then I want to maximize the entropy, then I can get the canonical distribution or probability density, probability distribution, and canonical and grand canonical. Okay, so microcanonical ensemble means your probability distribution is a constant or independent of I. Okay, and in canonical, this is something normalization factor, right? So it's basically proportional exponential minus beta EI. And in grand canonical ensemble, I have something that is over my grand canonical partition function with EI. Let's see, do I have this? Yes, mu n. Okay. Okay. So now I want to sort of derive this from a different perspective. Okay, so that's a sort of Lagrange multipliers. Okay. So if I want to maximize a function fx, however, there's a constraint that the gx has to be z0. Okay, so let's think about one variable problem first. Okay. Okay, so now we know how to deal with these problems. We define a new function which is a two variable. I can think about I have a function that has a two variable f, x, and lambda, which is the original function plus Lagrange multiply lambda and then multiply by your constraint gx minus g0. Okay. So I want to maximize this capital F. So basically, I have partial F, partial x 0, 0, 0, partial capital F, partial lambda equal to 0. Okay, so the first equation basically give you partial, and then I have fx plus lambda gx minus g0 equal to 0, and the second equation basically what you get is give you the constraint. Okay, so the second equation will give you a constraint. Okay, and the second equation modify your this partial your derivative a little bit so you can solve for this. Okay, so what is microcanonical ensemble? Okay, so basically I can say I want to maximize. Now let's see, if I want to maximize this function with the constraint, so here's my constraint, that my probability pi is normalized. Okay. So that function is basically minus pi log pi, and my constraint is sum over pi equal to 1. Okay, so now I can think about my pi is my independent variable. Okay, so that means the equation I want to solve is partial pi will now over my original function plus the Lagrange multiplier and sum of I pi minus 1 equal to 0. Okay. Okay, so in this way, then what I get? So basically what I get is kb log pi right minus kb pi and the 1 over pi plus lambda equal to 1, 0. Okay, so you can solve for this and you find this pa kb minus 1. Okay, so indeed it is independent of I, right? So as we expect the microcanonical ensemble, your probability is a constant. Okay, so what the exact value? So this lambda is fixed by requiring sum over pi equal to 1. Okay, so that means n lambda kb minus 1. Okay, so the key observation here is if I want to maximize the entropy function with a constraint that your probability density is normalized, then you will get the microcanonical ensemble, that is your pi is a constant. Okay, so now we just extend this. So now if it's a canonical ensemble, then actually I have two constraints. The constraint, my probability is always normalized. And also I want my average energy is certain specific energy. So average energy is sum of EIPI, right? So that's your energy expectation. Okay, so essentially then what this will modify our condition, right? So it will be entropy function plus Lagrange multiplier of the first constraint plus Lagrange multiplier of the second constraint. Okay, so the first constraint is related to the probability normalization, and the second constraint is related to the energy you constrain. Okay, so now if you solve for this equation, you'll find this pi equal to okay. So now the key observation is it's proportional to something related to EI. Okay, so it's inside in EI as I dependent. Okay, so I can connect this to canonical example. So apparently the prefactor should be one of partition function, and this should be minus EI divided by KBT. So that means my partition function is exponential 1 minus lambda KB, and the temperature is nothing but 1 over omega. Okay, so okay, so that is very simple. So you maximize your entropy function with two constraints, then you get a canonical probability distribution. Okay, so now it's straightforward for a grand canonical partition function. Then you can figure out you have three constraints. The probability is normalized. You have an expectation value of energy to be E, and your expectation value of your particle number to be N, right? So then to maximize this entropy function, then you have to assume your probability distribution satisfies this constraint equation. Okay. And then you will see that this PI is actually indeed your grand canonical partition functions probability, your grand canonical probability distribution function. Okay. Okay. So that let me see. Okay, so what else? Okay, so there's something else. Okay, so that is more or less for the part that I want to review before the exam one. Okay, so now we'll move on to that something still related to the quantum mechanics. Okay, and so now let's back to quantum. Okay, so let's have a 10 minutes break. Let's come back at 3:20. Okay. Okay. Okay, so let's resume. Okay, so now for quantum, when I have a quantum mechanics. Okay, so practically there are many things. Okay, so the easy so 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 how do I go from a classical formula to a quantum formula? Okay, so if you encounter an expression, then basically for quantum mechanics, we know that the eigenenergy is special. Okay, so if you have eigenenergy state, and so the energy level is En and En. Okay, so essentially it's the same. Okay, so then basically it's the same that, for example, for the that mean for canonical ensemble, well, for microcanonical, sorry. Basically, this is a constant. Okay, and for canonical, okay, so you can think about the probability the system is in any state n, psi n, or that is basically the same as it is in the with energy En, would be basically 1 over partition function. Okay, and in grand canonical, your probability okay. Okay, so here okay. So here basically you have a wave function. Okay, but the thing is basically for each energy level you have a connection that with the energy. You have an energy level and you have a wave function. Okay, right. So basically you have a harmonic. This is the eigenenergy. Okay, and if you have the particle number, then you have a particle number. You can basically count the particle number of this state, and you will have certain it's the eigen state. Okay, so that is the first step. You can connect these. Okay, but then you want to write this everything in terms of quantum mechanics. Okay, so then the easiest way is how do I get this En? So En basically is something that you have Hamiltonian, right? So if your Hamiltonian act, on eigenenergy state just become a number. Okay. So you think about if exponent minus beta h, then you act on expectation value, and this will give you basically En. Okay, so you connect this exponential of beta of your energy to a operator, the expectation value, quantum expectation value. Okay, so this is the quantum expectation value. Okay, so this is what you learn in quantum mechanics. Okay, how do I get the expectation value from some operator and some state? Okay, because now you have picked up the eigenstate, so everything will be easy. Okay, so if you do this, then the trace of operator is the trace of is basically sum any yes I is any complete basis. Okay, so what's the trace of exponential minus beta h? Okay, and now I can choose use my energy eigenstate as my basis to perform the trace. And this would be right. So this is my canonical partition function. Okay, so that's how we can make a connection. The first step, you basically write down your classical formula, and you interpret this energy as the eigenenergy of your eigenenergy state, and you make this connection. Okay, and the second, you make this connection, this result to the quantum expectation value of certain observables. Okay? So that means if I take a trace of exponential minus beta with Hamiltonian, you get the partition function, canonical partition function. Okay, so that's okay. And similarly for the grand canonical partition function, you can do this in a similar way. Okay. Okay, so now there's a confusion about what this is a mixed state. Okay, so let's forget about the statistical mechanics for a while, and let's think about quantum mechanics problem. Okay, so I know I can have a product Hilbert space. Okay, so how do I understand that? So suppose I have a system. You can have two sides. Side I and side 1 and side 2. Let me see. No, okay, I'm not going to this way. Okay, so suppose I have some wave function that live in the Hilbert space A. Okay, so I have some system A, which is described by a wave function A, and I have a system B that described by a wave function B. Okay. Okay, so I can have a product with product space. Okay, so then I can think about some wave function in this product space. Okay, so simplest example is a two spins system. Okay, for the okay, for I have spin 1 and spin 2. For spin 1, I have a basis which is S1, which can be plus or minus. For the second spin, I have another basis, so that is called SZ basis, and this is for the side 1, and SS basis for the side 2, which is also plus or minus. Okay, so now for this two spin system, then I can have a product basis. Okay, so that's S1, SZ1, SZ2. Okay, so basically have the plus plus, plus minus, minus plus, minus minus. Okay, so what is the most general two spins wave function? Okay, so any wave function basically can be written as the linear combination of the product basis. Okay, and you can probably normalize your wave function. Okay, so now you can do all the quantum mechanics operation on this two spin wave function. Okay, so now imagine an extreme situation that spin 1 is on Earth, spin 2 is on Moon. So in principle, you can have a product wave function of spin 1 and spin 2. Okay, but somehow if I only care about I do the experiment on Earth, okay, so that means I only care about the operator expectation value that live on system 1. Okay, so you can think about it's always basically product the identity operator. Okay, on system 2. Okay, so in principle, what I need to do is I plug in this operator to this general formula, right? So basically, I have this. This is like a sum over S1, S2, S1, S2, O1, S1, S2. No, okay. Yes. Okay. So, but since my operator doesn't care about the state in side 2, okay, so it's something related to So I want to write this as some expectation value relate with psi 1 only. Okay. Okay. So in this case, I can think about maybe I can only write this is something related to psi 1. So I want to define something that only depend on 1. Okay. Okay, so at the end of the day, I want this to be the same as something like this. Okay, so the problem is, can I do this or not? Okay, okay, so in this case, then this is so-called the okay. Okay, so recall that for pure state, so for any wave function, okay, so I can define the corresponding density matrix, which is something but this. Okay, so for expectation value, I can write this as a trace of this operator multiplied by this row and trace. Okay, so this is pure. Okay, so we have the, you can easily check this row square is which is okay. So this is basically so what happened to us. So we so-called the pure state. Okay. So now go back to our example of product space. So suppose I have something, a wave function that is a product, a wave function on product space. I can define a product space wave function. Okay. And for any operator that live on this product space, I can do the same thing. Okay. So now if this operator only live on space 1, let me see what I want to express here. Then then what I want. No, okay, okay. Let's see. Okay, so we can perform this is so-called partial trade. Okay, so you can imagine here this trace is over a product space, but somehow this operator inside didn't this O doesn't care about the second space. Okay, so you only do now if I sum over the degree of freedom of the second space on this total density matrix. What I get basically is sum over S2 Okay, so I call this is the so-called reduced density matrix on side 1. Okay, okay. So apparently this is will act only on the side 1 space. Okay, so if I do this, then basically I can have this. If this operator only live in the first space, then I can write this as O1. Okay. Okay. So let's without going into the detail of this operation, what's the key point here? Okay. The key point here is this total space is we only deal with pure state. Okay. And in pure state, I can steal the pure state. For pure state, I can have a density matrix operator. Okay. So now if I only consider part of the system, okay, so I have subspace. Okay. So then I can construct by tracing over partial, this is called partial trace, where I only trace over the degree of freedom of the system 2. Then I get so-called reduced density matrix. Okay, and we are in the later we'll sort of forget about this the reduce in front. Okay, and in this way, then you will get the mixed state. So in general, this will be mixed state. Okay, again, we are not going to a detail right now. Okay, so you have mixed state. Okay. So the lesson for this is this mixed state reduced density matrix not something that it's not something mysterious. Okay, so you only need to think about you have a combined system. Okay, and now imagine that you don't care, you only care about the expectation value of one of the subsystem. Okay, so you can think about the wave function on Earth and on the Moon. They are your combined system. Okay, but when I do the experiment, I only care about all the measurement operator is act on the wave function of the Earth. Right, so in that case, if I have some pure, I have a wave function that describes the product space of Earth and Moon. Okay, so but when I do the measurement of the Earth observable, then I do partial trace over the degree of freedom associated with the Moon. Then I get the reduced density matrix of the Earth. And then when I need to do any calculation, I just use this reduced density matrix multiplied by the operator I want to calculate and take a trace, but now this trace is only on the subsystem degree of freedom. Okay, so how is this connected to our quantum statistical mechanics? Okay, so now you should go back to the section where we derive the canonical ensemble with partial trace. Okay, so now remember, now this is again. So how do I get my canonical ensemble? So I have a total system. Okay. So I have a total system, and then so if this is a heap S, and this is a system. Right? Okay. So and I allow the system and the base to exchange energy. This is what it is. Okay. Okay. So now if I only care about certain expectation value on my system, okay. Okay, so remember how do I do this? Okay, so I have an omega function for the total system, and I say this is something that is dE1 omega E1 omega 2 E minus E1. Okay, but I only care about the expectation value of B that is on system 1. System. Okay. So then this is something like omega E over dPq dQ1 BP1 Q1 omega 2 E minus H1 P1 Q1. Okay, so the only assumption we have is 1 over T is partial S partial E2. This is fixed. Well, so we assume our base is so huge that as we exchange the energy, the temperature does not change. Okay, and then we go through a certain derivation, and then we can show that this can be written as our partition function dp1 dq1 b exponential h1 p1 q1 kbt, right? So basically this gives us the canonical probability distribution. Okay. Okay, so basically you can sort of go through the same derivation, right? So now you have a total wave function. Okay, so which is you don't know how to write it. It's very complicated. Okay, but your space is basically a system space direct product with your base. Okay, so you have the same assumption that so you can the total system can be described maybe by certain wave function. Okay, but now you only care about the expectation value of some variable at your system. Okay, and so for the derivation above, you can convert everything to a quantum mechanics. Okay, and at the end of the day, you will find that this would be something that is one of partition function trace of, okay, and your partition function is trace. Okay, and so you can think about this as your reduced density matrix is. Okay, so you basically combine two concepts. The first concept is for a product Hilbert space. You start from a pure state in the product space. You can perform a partial trace to get rid of the degree of freedom of your some of the like systems, some of the part, and then you have a reduced density matrix of the part you concern. Okay. So now if you apply this idea and you consider a total system, which is a product of a system and a product of heat bath, and you perform in your total system a microcanonical consideration. Now you do a partial trace over your heat bath because you are going to only to calculate expectation value of an operator that only live on your system. Then you will, by the partial trace, you will get some kind of a reduced density matrix of your system. Okay, and if you go through the derivation carefully, then you can show that this reduced system is going to be your canonical partition function. And if you write that in density canonical density matrix, okay, and you can write that as the exponential minus beta Hamiltonian divided by your partition function, and where your partition function is nothing but the trace of your exponential minus beta h. Okay. So I think this is sort of the one of the angle to see this is first you see how do you connect a classical expression to an expression that in quantum mechanics but only use an eigenenergy basis. Okay, but you want to express this in energy basis independent way, so you want to convert that into a operator, and that operator will involve your Hamiltonian. Okay, because when your Hamiltonian act on your eigenbasis, you only get eigenenergy. Okay, and the second thing is if you think about our derivation of a canonical ensemble is we have a combined system, but I don't care about my heat bath. So, and I want to derive in this what is the effective probability distribution of energy in your system, and you find that you satisfy this Boltzmann weight. All right. So now if you do the same calculation using quantum mechanics, you have a total system, you have certain wave function, and you put a partial trace over your heat bath, then you will get the density matrix of your system, and it's going to have this particular form that is connected to the classical partition function. Okay? Okay, so there's one more piece of information, so that is okay. So now we have this concept of total system partial trace, and then I have okay. So I know okay. So total system to a subsystem. Okay. So I have a pure state. So then I have a pure density operator. Pure density matrix operator. And I do a partial trace. Then get a reduced density matrix operator. Okay. Okay. So the confusion is for the reduced density matrix operator, it can be pure or mixed. And what's the difference between those two? Okay. Okay, so what's pure? Pure is very simple. Pure means that you can always write as a wave function cat multiplied by bra. Okay. So if I do a partial trace, then I get reduced density matrix that is on space 1. Okay. So if this reduced density matrix can be written as some wave function that live only on space 1, then I say this is pure. Okay. Okay, so if it cannot, then I can, this is mixed. Okay, so that is an important concept. If you have a total system, you do a partial trace, then you, in principle, by definition, you get the reduced density matrix. Okay, however, that most of the time, this reduced density matrix will be mixed, but it can be also be pure, because if there's no interaction between your two systems, basically you can still get a pure. Okay, so now the question is how do I see those two? So now I only, so what's the most general? So how do I express a reduced density matrix of your system 1? Okay, right. So basically, the system 1 has a, like if I have a spin up and spin down, right? So basically, I have a plus plus. Okay, so I'm going to construct the example another way. Okay, so for example, if I consider the hyper. I can have it. So that my density matrix is 1/2. Okay, so I have 4 terms. Okay, so the lesson here is like it has 4 terms, but I can arrange those 4 terms so that I can define certain wave functions so that this density matrix is the pure one. Okay, so now if I remove some of the terms, right? So then you can show that you can never be say something that is so what's the most general wave function? So you can try to solve this. Well, I can have alpha plus beta, okay, with proper normalized alpha beta. Okay, so the thing is then there's no solution. Okay, so that means this density matrix cannot be expressed as this simple wave function. Okay, so that means this is a mixed and this is a pure. Okay, so density matrix can be mixed or pure. Okay, and I start from a total system. I have a pure total system with some wave function, which right. So the total density matrix is pure, and I have a base, and I have a system. Okay, so I do a partial trace over the base of this total density matrix. Then I get the density matrix of my system. Okay, so if you do this operation, then usually this system density matrix mixed. Okay, but there are special cases they can still be real, pure. Okay, so that's you can do all kind of operation, and in quantum mechanics, that means for canonical ensemble, if you do this derivation, what you will get is your system will be in a mixed density matrix, and this density matrix is exponential minus beta h with the normalization function 1 of your partition function. Okay, and your partition function is trace of this, and this only live on your space 1. Okay. Okay, so I think the key message here is by you go back and read the derivation of this partial trace, okay, using classical mechanics. Okay, so now you imagine, you don't really need to go through the detail, you imagine you perform a similar calculation with a total quantum system. Okay, so that conceptually you will end up with some reduced density matrix of your system only, And if you perform a setup that will give you a canonical distribution, then you can show that this reduced density matrix of your system will have this particular form, and this particular form can be motivated or suggested by the connection to the classical expression when you consider the energy eigenstate of your quantum mechanics. Okay. So I hope this give you some overall picture. Okay, so I skip many sort of technical detail. Okay, here, but the hope is that so you don't feel this density matrix operator very mysterious. Okay, so you can think about the counterpart in classical mechanics, and you just perform the similar calculation in quantum mechanics. Then you can get this result. Okay, so due to the nature of the quantum mechanics, then this operator has this specific form. Okay, and okay, so then maybe next time we can review again how this connect to, because you have two different probability. You have a classical probability and you have a quantum probability. Okay, so I would suggest you to review this this part this week. So then in next week we can talk about this confusing concept that you have a classical probability distribution of Boltzmann way, and also you have an intrinsic quantum probability expectation value calculation. Okay, and to end, let's remind everybody again that we'll have an exam on the May the 7th, and it will cover the range chapter 1, 2, 3, 5, 6, and please wear a mask and come to the room. Go to your pre-assigned C. Okay, so we'll give you the C assignment before the exam by the email. Okay, and that is for today. Okay, see you next week.